Good day, viewers all over the world. Today we want to look at another solution of first order differential equation, which is exact equation. Exact equation is one of the equations that we have in first order differential equation. So a differential equation, as it is a differential equation, is a differential equation mx comma y dx plus nx comma y dy is equal to 0 is exact. How do we know that is exact? If there exists a function g x comma y such that that differential equation, the g x comma y will be equal to the given differential equation, and it's named equation 1. So if we're able to rewrite it in this form, then that differential equation is as an exact equation. So how do we test for exactness? How do we know if the differential equation, first order differential equation, is exact? What we do is that what we have beside the x here is mx comma y. So we are going to differentiate this partially with respect to y. The one beside x, the x, we differentiate it partially with respect to y. If it is equal to n of x comma y, which is beside the y, we also differentiate that with respect to partially with respect to x. If once we are sure that that differential equation is exact, if we are sure that that differential equation is exact, then how do we solve the differential equation? How do we solve the differential equation? This is what we are going to do. We find partial, we equate the given differential equation, which is equal to 0 here. We equate it to be equal to the g of x comma y. So how do we now solve this partial differential equation? How do we solve this? What we are going to do now is that under this, we are going to we equate what we are given as the g of x comma y. Then we differentiate that with respect partially with respect to x. We equate it to be equal to m of x comma y. Then we also have the g of x. We equate that as n of x comma y. At the end of the day, the solution will be of this form. The solution will be of this form. So I want to give an example now, so that we'll be able to understand all that I've been saying. That is, we first test for exactness. If I give you first order differential equation, how do we know that the differential equation is exact? We differentiate partially what we have beside the x here. Differentiate it partially with respect to y. What we have beside the y here, differentiate it partially with respect to x. If they are equal, then it shows that the given differential equation is exact. That's how to test for exactness. Then once we know that they are exact, then we go ahead and solve the differential equation. So let's give example. In order to buttress this point, I'm going to use a particular example to explain better, so that we understand what I'm saying about partial differential equation. So let's take example. So let's say this is example 1. Example is 2 in 1. The A part of the example, the differential equation. We have to determine whether the differential equation is 2xy dx plus 1 plus x squared dy is equal to 0 is exact. That's the first part of the question. We want to determine if this differential equation is exact. So if it's not exact, then we don't need to bother ourselves. But once the differential equation is exact, then the question says that if it is exact, if this differential equation is exact, solve the equation. So the question is in 1. What is the differential equation? 2xy is exact. We want to determine if this differential equation is exact. So what do we do? How do we determine if this differential equation is exact? That is what I'm about to do now. That's what I'm about to do now. Then how do we test for exactness? What we have beside the x, we call it m of x comma y. And what we have here is 2xy. Then what we have beside the y, we call it n of x comma y. And that is 1 plus x squared. That's what we have. Is 1 plus x squared. That's what we have. So what do we now do here? What do we do? What do we do here? What we are going to do is that we are going to differentiate both m and n partially. The first one is that we differentiate m partially with respect to y. That is, we say the m. We are going to differentiate this, the m, the y. If we differentiate this partially with x, we are going to have 2x. Okay, that's what we get. Then the second one, we differentiate the n with respect to x. If we differentiate this with respect to x, partially with respect to x, we are going to have 2x. We realize that the m, the y is same thing as what? The n, the x. Then if these are equal, this is the condition for exactness. Since we are able to derive that the m, the y is same thing as the n, the x, then it shows that that differential equation is exact. So the differential equation is exact. So we have been able to solve the first part of the question. We have to determine whether this differential equation is exact. What we are going to do is that what we have beside the x here is, we call it m. Differentiate it partially with respect to y. What we have beside the y, we call that n. Differentiate it partially with respect to x. The x, the one beside the x, you differentiate partially with respect to y. The one beside the y, you differentiate partially with respect to x. If we are able to get the same thing, then it shows that that differential equation is exact. Now that we are sure that the differential equation is exact, we can go ahead and solve the differential equation. So how do we now solve this differential equation? That's the big part of the question, and that's what we are about to do now. So how do we solve this differential equation? That's the big part of the question, and that's what we are about to do now. So how do we solve the differential equation? That's what we are about to do now. For us to be able to solve this differential equation, then the following step must be observed. The following steps. The first step is that we are going to we are going to find the g. You know, if you want to solve this, we equate everything here. So g of x comma y. That's the other method of solution. So we are going to, what we are going to do is that we are going to have the g. We are going to have the g, partial derivative of the g, the x, to be equal to m of x comma y. Then m of x comma y here is same thing as 2xy. Okay. Then the g, the y, we have it as n of x comma y, and that is going to give us 1 plus x squared. That's what we are going to get here. That's what we are going to get in that second one. That's what you are going to get. So that's what you are going to get there. So thereafter, from that first one,